So, to the topic at hand, before I run out of time for all of you, what makes small fields so challenging? And number one really is size. It's fairly obvious, but it's something that we need to talk about when we're addressing these small field challenges. There are other factors that play into it: source occlusion, changes in the energy of the field, or scatter energy, shape and location of penumbra and how that impacts your field shape and your measurement itself, loss of lateral charge particle equilibrium, these sorts of things that I will be talking about in the next few slides. I'm leaning very heavily on a couple of excellent references that I would recommend anybody getting into small field dosimetry or trying to really shore up their own program. Take a look at these two references. So the first one is the IPEM report 103, small field MV photon dosimetry. And the other one is that joint publication from the IAEA and the AAPM, that is TRS 483 on dosimetry of small static fields for external beam radiotherapy. So TRS 483 defines small fields for us. It defines them as having at least one of these three conditions. You have loss of lateral charge particle equilibrium on the beam axis, and or partial occlusion of the primary photon source by your collimating device, again on the beam axis. And number three, the size of the detector is similar to or large compared to the beam dimensions. And this is the one that people tend to overlook when they're picking a detector and trying to determine where it fits on the flat part of their field. So this is one that I do want to emphasize, that if you have a slightly larger field that you feel is not so much a small field, but you're using a big detector in it, it can still meet those small field conditions and needs to be handled carefully. So number one, as I mentioned, is physical size. That's the first challenge. Usually we're talking about somewhere between 4 millimeters and 4 centimeters. So the first question to investigate when you're looking at your own small fields is, how are you defining that field? Are you defining that field by where the jaws are being placed with your accelerator, with your MLC, high definition MLC? Or are you using a stereotactic cone where it's defined more by the full width half max? If you are looking just at jaw position, that can affect the overall shape and size of your field. This is one of those images from actually from InterDOS, showing if you have a larger field, you have this penumbra shape that is formed by the jaw or the MLC at the side of the field. And when these two jaws get close enough together, now you get an overlap of that attenuation at the penumbra, which actually decreases the output of your field, increases the full width half max beyond what that jaw setting is. So those things need to be considered when you're picking a detector or when you're trying to define these fields. The other thing about physical size is that alignment matters so much more than it does in the larger fields. A very small misalignment means a very large geometric or dosimetric miss or error. Source occlusion, if you don't know what this is actually a blocking of the primary fluence from the source. So from the IPEM report, I can't talk today, we're looking at if the jaws or the MLCs are set wide enough, then your measurement point has direct line of sight visibility to the entire source where the X-rays are being generated. There's this penumbra region where you have scatter or secondary, where you see only a part of that primary source, but here in the center you actually see the full output. You see the full geometric, I guess, totality of the source there. Once these MLCs come in farther, you start blocking off some of the edges of this in terms of the direct line of sight from your measurement point, and your detector may be affected by this source occlusion. The scatter from your primary collimator and from your flattening filter is reduced for these small fields as well, but the key point with source occlusion is that small enough fields also reduce the direct beam fluence. The third challenge, lateral electronic equilibrium. Generally, this equilibrium condition is that your lateral scattering distance has to be equal to or greater than the range of electrons that are being set in motion within the medium. So if we do a practical translation of this, you may start losing lateral equilibrium when your beam width is at or less than 2 times your Dmax depth, because you're looking at scatter from both sides. Your higher energies actually lose their plateau sooner, is the other implication there, because as you go down in field size, you cross that threshold of that scattering distance a little bit sooner. So your detector positioning, your perturbations, all of that comes into play sooner for these higher energies than it does for the lower energies. So it is also important then to characterize the profiles of your beams, not just the output factor. It's also important to consider the impact of putting some different density item within that beam, because it will affect the lateral scatter. So that brings me to my next topic: how do the detectors themselves impact the measurement? So far, we've just talked about kind of conditions of the beam, but the detectors themselves also impact these measurements. So the first thing, again, is size, detector size, and the shape of the detector. If you have a round detector like I'm showing here, then it's uniform in terms of its volume averaging in both dimensions in your field. If you have an elongated detector like the one shown on this side, now you have volume averaging over a shorter distance in one axis and a longer distance in the other axis. So it's something to be aware of as you're positioning this within your field, or planning which fields you could use your detector for. So you have to be consistent, of course, and accurate with the positioning of your detector. So again, a small offset can make a major difference in the accuracy of your measurement result. This plot on the right-hand side is actually one of my favorite illustrations of considering the totality of your detector and not just where that active volume is. This is from a publication from Meltzner and DeWord a number of years ago. I guess it's 15 years old now. But they were looking at gamma knife helmets and the output from the gamma knife at these various field sizes, and assuming at first, of course, that the size, the active volume of the detector meant that you would have some volume averaging for the smallest 4mm helmet, but that you should be within the plateau for the 8mm helmet, and came to realize through the course of the investigation that you actually needed to consider these lateral scattering regions, the buildup cap, or lateral scattering distances on each side of that active region, and they were actually seeing some effect from the lateral scattering decrease from the 8mm helmet as well, even though it looked like from the detector size, just the raw detector size, that it ought to be fitting within that flat region. So very much impacting the measurement, how big your air volume is, or your different density within that small field. If you're using film, for larger fields, film is a good way, or well, even for small fields, to get profiles, to determine penumbra or field shapes. If you go down to the extremely small fields, the light scatter within the scanner itself can affect the scan, can affect the resolution there. So something that you may want to characterize your scanner for, or at least be aware of, that for extremely small fields, you may not read the full density that you should be reading. Spot readers are kind of good for double checking that. Second way that the detectors impact the measurement is actually perturbation of the beam, which affects that lateral scatter part too. Again, depending on the size of the differing density from the surrounding material. So what's really happening is that you're perturbing the fluence right at the point of measurement. So the way that beam is interacting with the material changes. So you're altering the dose by replacing water or water equivalent material with the detector itself. So the things to ask when you're picking a detector for these measurements: if you're looking at an ion chamber, how big is the air cavity? How big a region are we actually decreasing this density over? If it's a diode, what's the density of that diode? But also, is my diode compensated? So because these solid state diodes are more dense than water, sometimes there's a built-in low density region right next to the high density region to try and average out that perturbation. The question is, at what energy is that compensation accurate? And how does that change the energy dependence away from the targeted design energy? Diodes also very frequently have energy dependencies. So knowing if you have one that varies very quickly, or that's a little bit less energy dependent, is important as well. There are published corrections sometimes available for these detectors. There's one from Paulo Frasescan shown at the right here. The critical part with published corrections is that sometimes these are very specific to the configuration or the setup or the energy that was used in the publication. And so it's important to match the published correction, or match the conditions of the publication in order to apply these corrections to your measurements. And if you're close, or if you're not matching them, then you might need to do a little more digging to try and figure out what implications that has for your measurement. So another publication here from Paulo Frasescan showing just the fact that these diodes and our scintillation detector diodes over-respond because of that higher density, and so their correction factors are less than 1. Ion chambers over here on the right under-respond because they are lower density. You get less energy deposited when you're perturbing the beam like that, so their correction factors are greater than 1. The signal level that you're getting from your detector can affect the accuracy of your measurement. So with ion chambers, signal is proportional to the collecting volume. So as your volume decreases, your signal decreases as well. So signal to noise ratio becomes much more of a concern for ion chambers in these, or for very small ion chambers, especially in very small fields. And then your small signals from these ion chambers require an appropriately sensitive electrometer. So if your electrometer doesn't have a good low range, or has a higher noise floor, that will come into play with some of your measurements as well. An advantage of diodes is that you do get a larger signal from them than from the microionization chambers. Of course, there are trade-offs with those as well, but that does help with signal to noise ratio if that's a problem for you. In looking at your SNR, it's important to consider leakage, to really evaluate the leakage from your system, to have a proper electrometer warm up so that everything electronically is stable, so you're not adding additional noise or additional current from just the fact that the components themselves are warming up. It's important to match the signal strength from your detector, whether it's diode, ion chamber, or scintillator, to the proper electrometer range that you're using. And one that was new to me when I got into this to the small field realm a number of years ago, but was actually that you can induce effects if you're not taking care of your triaxial cable properly. If you have a cable that is all wound up tightly and you've just strung it out to start your measurements, there's actually some physical relaxation that can cause a current to be generated through these triboelectric effects. And it can take up to 3 hours for that physical relaxation of the cable to stabilize and not give you a little bit of background current. That's generated as it's relaxing. So a system that will never hold at 0 may be a clue that you need to wait for your cable to relax, or if your cable is old and damaged and kinked and twisted and all of that, don't use it for small fields. Use it only when you have big signals. And actually, I'd cringe a little bit if you use it then too. But it's important to have good quality, well cared for cables for these measurements. A cable that's damaged can be improperly shielded, which may also induce additional signal if there's cable being irradiated in the room, even just scatter irradiation. So having good quality, well cared for cables is important. The detectors can impact the accuracy of your measurement as well. So energy dependence shows up in a number of detectors, particularly solid state detectors like diodes. They actually give you a low response out of the field, which can cause an underestimation of a large region of low dose if you're using that for your treatment planning system. Compensated can be good or bad depending on the energies that you're looking at and whether you're using these for depth dose curves, getting that change in the scattered energy, as well as the change in energy just with the primary beam at depth. So for a detector that has a high energy dependence, you may actually have depth dependent corrections in order to account for that. And if there are differing scatter conditions, that can affect the response of the detector as well. If there's an angular dependence for your detector, that can affect your accuracy. So I always recommend that people use a detector that had in the orientation that it was designed for, or be aware of implications of using it in a different orientation. It may take a little more investigation on your part to make sure that readings are accurate. Some detectors, particularly ion chambers for this one, but detectors can have dose rate or dose per pulse dependencies. If you're moving into the flash realm, dose per pulse becomes a crazy topic, but there are some dose per pulse dependencies that can happen just with a standard FFF linear accelerator as well. So this requires an understanding both of your accelerator and of your detector. Does my detector have dose per pulse dependencies or dose rate dependencies? And does my accelerator turn up the pulse rate in order to give me a higher dose rate, or is it actually changing the dose per pulse that comes through? And I put in a et cetera category. There are other things that may need to be considered depending on the detector that you're using. What's the leakage? Does it drift? How repeatable is it? What's the resolution that I get? Can I calibrate it? We've talked about some of these ion chambers, diodes. This is our scintillator, but there's film, there are TLDs and OSLDs, there's the radiochromic gels. There are other tools that can be used for this that each have their own potential pitfalls, but have things to be considered. So with all of those potential pitfalls, really, what are we supposed to do? It sometimes feels a little bit overwhelming. But I'm happy to tell you that there are options. These are some options that work well for megavoltage beams. We have some established technology with known perturbation issues. Those would be diodes. We have some newer technology. They've been out on the market for a while, but it's new to a lot of people, and that's the plastic scintillation detectors, the X-ray in W1 and W2. And then we have the old standard, the ion chamber. That's actually working properly in miniature form. It took a number of years for that to happen as well. Again, this has been on the market for a while, but is not something that some people are as aware of. So every detector has both strengths and limitations. The best solution for small field measurements really is a good combination of detectors. So if we look at standard imaging's X-ray D1V and D1H diodes, it's the same silicon diode in two separate housings. One is designed for scanning, so that would be the vertical one here in order not to have the water perturbation as you're moving that around. Scanning can get nicely up to the surface. This one in the horizontal housing, the D1H, is designed to be used with slab phantoms, so the channel can be milled out a little more easily for positioning of that one. They are unshielded diodes with a 1 millimeter diameter active spot size, and there are published corrections available. This one in particular is actually two publications in 2014 looked at both measured and calculated factors. So this is one from Papakonstantopoulos, and then this one is one from Paulo Francescan. So strengths of our diodes, they are well-established technology. Diodes have been used, these diodes in particular have been used for years. You can use them for scanning your small fields. They do have minimal volume averaging with just that 1 millimeter active area. And they have low angular dependence. So as you're scanning, of course, with small fields, you don't get nearly as far off axis, but as you're scanning, you don't have to worry as much about angle of incidence of the beam. Limitations of our diodes really are limitations of any diodes that you're going to encounter. They're not water equivalent because they're a higher density material. So they do require corrections both for that energy dependence and for the density, and they do have a little bit of angular dependence. The second option I would propose are the X-ray and scintillation detectors. These have been serious game changers for small field dosimetry. They're water equivalent organic scintillating material, and we have options for 1 millimeter by 1 millimeter or 1 millimeter by 3 millimeters long cylindrical active region. The tricky part with scintillators is that you do have to correct for the Cherenkov light that is generated in the optical transfer fiber that carries the light from the scintillator to the optical detection system. They're also not NIST traceable calibratable, so you have to cross calibrate them or daisy chain them with a calibrated dosimeter or a calibrated ion chamber, and then recalibrate them periodically, both for the CLR here stands for Cherenkov light ratio, the correction method we use for Cherenkov, as well as a dose calibration as the material accumulates dose. So I think most of us have seen old PMMA phantoms, old clear plastic phantoms that have been irradiated a lot. They start to turn yellow after a while with all of that radiation dose, and the same phenomenon affects our optical measurements with the scintillation detector. So that decreases the signal that can pass through the yellowed fiber and also changes the spectrum slightly, which changes how we would correct for the Cherenkov. The method that we use for our scintillation detectors to get rid of Cherenkov light is a 2-channel chromatic correction published by Guyot et al. In 2011. But really, we're splitting the light into a blue section and a green section. Our scintillator is a blue scintillator, so most of that signal falls within the blue region. Cherenkov is a broad spectrum contaminant light, the STEM effect basically kind of light that falls across both the blue and the green channels. And so in order to characterize your fiber, we have you do 2 measurements, one with the fiber coming straight out of the beam. This is a jig that you can use in the water tank, or a solid slab you can use with a larger field. So we do a minimum fiber configuration with the fiber coming straight out, and then a maximum fiber configuration with the fiber wrapped around. So the idea with this really is that you keep the dose to the scintillator itself the same. So this blue curve from the scintillator does not change, and the Cherenkov component changes in both the blue and the green channels. So if we take the difference between the maximum and the minimum fiber, and for blue divided by that same change in the green channel, we can calculate a correction factor called the Cherenkov light ratio, or CLR, that can be used to remove Cherenkov from the rest of your measurements. So then your scintillation signal is your blue signal, where we have that scintillator signal, and then you subtract the green signal from that measurement times the CLR, and that gets you just the scintillation light from that measurement. If you do a dose calibration, you would give it, in this case, this has a 10 by 10 field marked on the slab, or you could give it a known dose at a smaller field in your water tank. If you give it that known dose at a reference field size, then we can create essentially a unit conversion, but a multiplicative factor that would take this scintillation signal from just a charge measurement that you've collected based on the light that came in to an actual dose value. One of the best things about these scintillators, and the reason that they're so popular, is that they do have a beam quality conversion factor of unity. So one of my favorite things out of TRS 483 is that every table that the W1 shows up in, all of the correction factors that are listed for all of the field sizes that are listed are all just unity. So it takes one thing off of your plate in terms of concern about, am I correcting this properly? And the W2 Actually, let's start with the W1, I guess. The way I have my slides, the strengths of the W1, again, that beam quality correction factor is unity. So it's water equivalent for these MV photons and electrons. It has not shown dose rates or energy dependencies for standard clinical beams. If you're talking flash, we'll talk that another time. We'll probably run out of time for that today. And it has a negligible temperature dependence. So there, if you're doing all of your measurements at room temperature, there's no need to correct for the temperature either. It's about 0.1% per degree Celsius that you might see a difference in signal. Limitations of the W1 is that this was our first generation simulation device. It was not designed for scanning or really for large fields. It was a small field output factor device. It's a low signal, so you get a low signal to noise ratio as well. There's a higher uncertainty out of the field in the low dose region if you were trying to do point measurements across your field. It does require a 2-channel electrometer like our Supermax. I don't think I've got that listed here. And it requires a reference dose or occasional recalibration. This is a relative dosimeter like a diode, and you cross-calibrate it or daisy chain it. Optical signal measurements are non-intuitive to many users, so there is a bit of a learning curve with this one in terms of being comfortable with it, being sure that you're trusting your measurements and feeling like you're doing things properly there. Once you get past that hurdle, it's a wonderful device. The W2 was our second generation scintillator. We were able to improve the sensitivity of our optics, so we could allow the use of a 1x1 millimeter scintillator as well as the 1x3 that is the same fiber as in the W1. But in order to decrease that signal to noise, to decrease our electronic noise, we combined the optics with the electronic signal processing system so that we can do point measurements with this device, and we can do a very fast Cherenkov correction for every 10 millisecond integration. We can convert that into an analog output and send the signal to your water tank scanning system. So for small field scanning, you can use the 3D tank that you have. That tank would just treat the scintillator as if it's a diode. You don't apply bias to it, but you get a signal when it's being irradiated. And our dedicated electrometer, the Max SD, is essentially just a pass through for that signal. So the way it looks in your water tank, you would have the W2 fiber with an adapter sleeve so that you can hold it in just a standard chamber holder. That optical fiber goes to the Max SD, which does that Cherenkov correction and then sends the signal to your scanning tank electrometer. You can do your CLR measurements or your dose measurements in the water tank, either with this the jig that we provide, or there's actually a rectangular field method that you can use as well in order to use it just in this scanning setup. So strengths of the W2, then we've managed to keep all of the strengths of the W1. It's the same fiber, so we have the same KQ, same advantage on dose rate or no dose rate and no energy dependence, same negligible temperature dependence. We've just removed a couple of the limitations of the W1. So you can scan with it now, and we have a better signal to noise ratio so that those shoulders of the field as well as the out of field signal can be captured accurately. In terms of ion chambers, our microionization chamber, the A26, was designed as as a result of Dr. Jessica Miller's investigation into the strange polarity and ion recombination that was happening in all microchambers that were on the market. And the result of that investigation is this ion chamber designed completely of conducting plastics, like most of our chambers are, but as small as we could possibly make it and still be repeatable and reliable. So it was designed to provide these reference class measurements for small fields. When we were designing it, there are a couple of different things that we were looking at. The chamber spot size, which would be this full region that's occupied by the active chamber plus its walls, was designed to be spherical. So the orientation of your chamber wouldn't change how the volume averaging was occurring, especially if you're scanning a penumbra. Does it matter if you're scanning forward and back or left to right? It doesn't with the 26. We modeled the electric fields to verify the shape and the volume that were there. We made the volume just as small as we could manufacture it. So our A16 has a wire center electrode. There's a little bit less manufacturing tolerance that has to go into that, and so we're able to make the volume smaller. But the spot size is still 3.5 millimeters. Where with the A26, our volume is twice the size, so you actually get twice the signal, which again helps your signal to noise ratio without compromising very much at all on the spot size. So we were definitely considering signal to noise ratio in some of those design discussions as well. Strengths of the A26, it was designed as a reference class ion chamber to behave in the way you expect a good quality reference class ion chamber to behave. Spot size is independent of its orientation. And really, ion chambers are familiar technology for most physicists. We're comfortable operating in this realm. We're comfortable with the corrections that need to go into it and the design or the troubleshooting that may need to happen if you're seeing odd behavior from it. Limitations of the ion chamber really are that it's an ion chamber. You're putting a low density region into your field, so there are some corrections required to account for the perturbation that happens when you put that air volume into your field. So I've had people ask me then, what about small kilovoltage X-ray fields? We do have an ion chamber for that as well, the X-ray in A20. So that's a low energy X-ray chamber designed for small radiation fields. It's actually a parallel plate chamber with one plate here and one here. So it's meant to be used end on, irradiated from the top or I guess aligned from the side, depending what you're doing. It works quite well for superficial skin therapy type beams. It has a not quite 2 millimeter diameter collecting electrode. And it has a very excellent energy response in that low energy region. If you're making measurements with these small detectors, whether it's the A20 or the A26, you need an accurate electrometer. We have, I'm sure most of you are aware of a very robust kind of workhorse electrometer, the Max 4000 Plus. Has a long history of very happy users across the world. And then, of course, we have the Supermax, which is our high-end electrometer with the touchscreen. It has dual channels so that you can make two measurements or you can intercompare two detectors at the same time. And it also has a very quick warm-up time, which is nice if you have to make measurements on the spur of the moment because something came up and there's something that needs to be investigated. And we stand behind our equipment. These are very robust electrometers. They both have an industry-leading 5-year warranty on those, just standard. So that's what I had. I managed to pull it off in a little more than a half an hour. I apologize for talking quickly. I know your time is precious. I'm so glad that you came here to listen to me today. I'd love to see you at AAPM. If you stop by the booth, I'll be in and out, but there's a schedule posted. I forgot to put the link here. Go to our website. You can reserve time to meet with us, with any of us, the sales team or physics. Or I may run into you in the hallway going to and from talks. Please stop me. Please say hi. Ask any questions. We would love to talk to you. So with that, I'll open the floor for questions. I don't see any yet. Maybe I'm looking at the wrong tab. Nope, I don't see any questions yet. But if you have questions, I'll stick around and we can talk about some additional questions. Otherwise, thank you so much for coming. And I look forward to seeing you at another time.